The final rule about integration that we are going to learn is called integration by parts. And look, this is the most complicated rule that I'm probably going to be explaining in our entire course. So I'm going to do it extremely slowly. We're going to start with derivations, and then I'm going to show you how the rule works in a couple of examples. But before we can proceed with this rule, let me introduce you a new concept. We already know what is a differential. Differential is simply very, very small change, right? And look, we were discussing thus far case where we have y as a function of x, right? And we said that dy, so differential of y can be calculated as dy dx times dx, right? Where this is simply derivative f prime of x times dx, right? So here we have very small change in x times derivative, so ratio of the two differentials is equal to the differential y. Now, why did we get such simple expression for this? Well, the reason is that we have a function of just one variable. Look, here x can be the only source of change in y. Okay, but now let's move to a more complicated case. Look, what if we would have a situation like this? That we've got some function. Let's just say that z is a function of x and y. So, how does the map of influence look over here? Look, we can have a situation that x and y both can influence z. But how do they individually influence z? Look, here we said that this influence can be measured by derivative f prime of x, right? But this time we've got a z that is a function of both x and y. So what do we need to use to measure it? Well, we need to use partial derivatives. So df dx, or simply fx, or df dy, or simply dfy, right? So look, now we have a situation in which there are two possible sources of change in z. One when x is changing, and one when y is changing. So how can I write expression for differential of z over here? Well, it's going to go like this. Look, first thing that can change here is x. So we can have change in x. Very tiny, right? Differential. So when x is changing by small amount, by how much z is changing, this, of course, is measured by partial derivative df dx. Now, but this is not the only source of change. The second source of change we can have over here is the source is change in y. So now we need to take into consideration there is a second possible source of change because both of these variables can actually vary. So now what is the measure of the impact of f of y on z? Of course, partial derivative of f with respect to f of f with respect to y. And look, this, what you see over here, is a total differential. Of course, look, the more variables we would have in this function, the more expressions like this we would have, because the more sources of change we would have. But all of those sources combined are giving us the total differential. So total impact of all variables or all independent variables, arguments in the function on the value of z. Okay, let me illustrate this with a very simple example. Well, let's just say that z is equal to 4x squared y cubed. Now, what is total differential dz? First, I need to calculate partial derivative of f with respect to x. So look, this time I'm assuming y is constant, so I'm getting that this is 8x y cubed dx. Now, I need to add to it partial derivative of z with respect to y, so I'm assuming x is constant, so I'm getting that this is 12x squared y squared dy. And look, this expression is showing us what will happen to z if both x and y are changing at the same time. Of course, look, we're going to be discussing this in the future, but if one of those is not changing, for example, this one is equal to 0, so only x is changing, then from this expression we can read actually change in z. And similarly, if this one would be equal to 0 and this would be different than 0, this expression would tell us by how much z is changing. Okay, so this is it about the introduction. And why did I introduce total differential to you? Because total differential is something that we need to use in the proof of integration by parts. Because once we know how total differential works, proving integration by parts becomes a trivial thing. But first, let me just write you down the rule. Integration by parts works like this: that integral of v du is equal to u multiplied by v minus integral of u dv. And this is one of the things you need to know by heart, unless you will remember how to derive it. Okay, so how do we arrive at such a result? Imagine a situation like this. Y is some function of two variables, u and v. And let's just say that this variable, this function, has a very simple form of u multiplied by v. Okay, what I'm going to do with this is that I'm going to calculate total differential of this function. And look, so df, right? So total differential, you change in the value of function f, or dy from our perspective, is equal to what? Derivative of function f with respect to u times times du plus derivative of function f with respect to v times dv. Okay, so look, now I'm going to write this expression a little bit differently, but I hope you can imagine why am I doing like this. Look, because f, function f, is equal to u times v, I'm going to write it as d u v, right? But you can imagine that there is a parenthesis in front of it. This is going to be important in a second when I'm going to be explaining all the steps. Okay, so now, if I'm differentiating this with respect to u, I assume v is constant. And look, I'm getting that this is just v. So I've got here v du. Plus, now, if I'm differentiating f with respect to v, I'm assuming u is constant, right? So I'm getting that this is just u dv. Okay, and look, we know that for this particular function, f of uv equals u times v, this is 100% true, by definition. So, what am I going to do next? Look, what am I going to do next is I'm going to integrate both sides of this equation. So look, what am I getting on the left-hand side is an integral of duv, and what I'm getting on the right-hand side is integral of v du plus u dv. Okay, now we already know that integral of a sum is equal to the sum of two integrals. So let's write it down. Okay, and look, now there is one problematic thing. How should I integrate this? And look, I could give you a simple answer. Look, because this is differential of u times v, then integral of duv must be equal to u times v. But even though this is 100% true, I want you to understand this a little bit better. And in order to do so, let me show you a very simple example that should prove it to you beyond any reasonable doubt. Okay, look. Integral dx is equal to how much? Well, integral of dx is equal to 1 times dx. Correct? Of course. Now, if I'm integrating 1, what am I getting as a result is 1 times x plus c, or simply x plus c. Okay, and now let's imagine a very simple thing. Let's just say that x is equal to u times v. What are we getting over here? Integral duv, which is equal to integral 1 duv, which is equal to 1 times uv plus c, which is equal to uv plus c. Look, actually, every time when we integrate 1 with respect to something, we are getting the same thing at the end. So, obviously, from this, we need to obtain u times v, which is equal to and now, of course, you might say, yeah, but you made a mistake. You forgot it about c. And actually, I didn't. Look, there is one thing I haven't told you yet. But generally, because c is an arbitrary constant, we don't know how much it is. We don't need to write it in any equation until there is at least one integral sign left. Because look, if I would integrate those, and I would get some results. Let's call those results m, n, and k, right? Let's just say that I'm getting m, n, and k. Each of those would be plus some c1, plus some c2, plus some c3. Now, of course, instead of writing those three, I can just put them all three into C1 to just C, and we would get that this is C2 plus C3 minus C1, right? So, as long as there is at least one integral sign in the equation, we don't need to add C, because C would be, this C would be melted with the new C we would get out of one of these two. And look, at this moment, we basically have integration by parts. So the only thing I need to do here is to change the order. If I'm going to solve this for integral v du, so move this to the other hand side of the equation, I'm going to get the integral v du is equal to u times v minus integral u dv, which actually finishes our proof and demonstrates that this rule holds. Okay, so now that we know how the rule works, how do we apply it? Well, at first it might seem complicated, but once we start, I think you'll be able to do it with much ease. Okay, so let's start with the first example. So we've got to integrate x times x plus 1 to the power 1 over 2 dx. Okay, every time when you see a problem like this, the first thing that should pop to your mind is maybe I can use integration by substitution because it's easier and shorter, more pleasant, right? But look, now if I'm going to say, for example, that k, I'm not going to be using u because u will be used for something different now. So if k is equal to x plus 1, then dk dx is equal to 1. And look, I have x over here. I cannot take x, which is a variable, out of the integral. I only can take out constant. So this will not work over here. So in situations like this, we are resorting to integration by parts. The way you see it over here. And look, this means that we need to establish two variables. One is v and one is u. And look, v is usually the one that it's harder to integrate, but there is no rule. But I can tell you one thing, if you choose wrong, you will know right away in the first line of solving, because you will end up with the same problem you were trying to solve. So there are always two ways in which we can approach it, but very often, like in this case, it doesn't really matter which one we choose, we're gonna get the same result quite easily. But in some situation, there are some specific ways of choosing it, and I'm gonna show you that a little bit. Okay, so look, in this case, I'm gonna choose that v is equal to x. So look, we've got a function v equals to x. Now I need to know what is dv. And look, dv is a differential of v with respect to x. Right? What is the derivative of v with respect to x here? It's 1. So I can simply write it as dx. Now, the second variable I need to choose is u. But look, u, unfortunately, needs to be an integral of the other part. So it's not that we're going to replace this with u, because in the formula now we need to have du. First, I want to integrate u. And look, if I'm integrating u here, then I'm getting that this is x plus 1 to the power 1 over 2 dx. Okay, and look, now, in order to integrate this, I need to use integration by substitution, of course. But look, this time, if our k or our u from before is equal to 1, we have 1 over here. So even without, rewriting it into steps, we can easily calculate that in this particular case, the integral is equal to x plus, let me write it like this, x plus 1 to the power 3 over 2 multiplied by 2 over 3. Because remember, every time what we have in power, we divide by the reciprocal. We divide by it, so we multiply by the reciprocal. And look, of course, here we would get also plus c. But of course, this is not going to influence anything, and we're also not going to use this c in the formula a little bit later. But look, what we can do now is to calculate du, which is of course equal to du dx times dx. And look, here we could calculate it, using the chain rule, but it's kind of pointless, because if this is the integral, then this must be, if this is the integral, this must be a derivative inside the integral. So our du is equal to x plus 1 to the power 1 over 2 dx. Okay, so now we have everything done, because we've created a set of possible substitutions. So now let's just substitute. So instead of x, we write v. Instead of this, we write du. And this must be, of course, equal to u times v minus u dv. Okay, and look, now we can start substituting back. U times v is going to be this times this, right? So we get that this is 2 over 3x times x plus 1 to the power 3 over 2. Now, minus. We open integral sign, and look, what we now need to plug in is u. Our u is this expression over here. So it's 2 over 3 x plus 1 to the power 3 over 2. Now, instead of dv, we write dx, which makes things very simple over here. Okay, look, I'm going to do one more thing here. I'm going to take this 2 over 3 out of the integral sign. So before the integral sign. And look, again here, I need to use integration by substitution to calculate this. So, in this case, I'm getting that this is equal to 2 over 3 x times x plus 1 to the power 3 over 2 minus 2 over 3 times. And look, now by using integration by substitution, I'm going to get that this is x plus 1 to the power 5 over 2 times 2 over 5. And look, now, because the last integral sign in the equation is gone, I add c. Okay, and look, now I can calculate this. I can actually simplify it by a lot. For example, I can take out 2 over 3 x plus 1 out of the brackets, and then I'm getting inside that this is x minus 2 over 5 x plus 1 to the power of 1, right? Because I've taken 3 over 2 outside the brackets, and plus c. Okay, we could also calculate this, but we're not going to do it because I'm not having more space on the blackboard and I don't want to use the blue. But as you see, this is actually a trivial task to do in here. Okay, I know it might be scary at the beginning, but believe me, once you do 10 of those, you will know how to do it quite easily. Okay, so now let's go to exercise number 2. And in this exercise, we're going to try to find a formula for integral of the logarithm of x. Okay, and now, look, here what we see is an integral of ln x dx. I have not shown you the formula for it. The formula for it actually exists. But how do we actually get this formula? Well, what we need to do is to calculate the integral. Okay, now look, here is the first problem we've encountered. Over here we've got just one component, not like here when we hit 2. So what should we do? Look, remember that even though this function over here looks like ln x, and it's the only one thing, I can always write it as 1 times ln x dx. So you see, I get the same thing, but I have 2 components. So one can be associated with v, one can be associated with u. Okay, what should be our v? Look, in this case, definitely the better choice is ln. Why not? Well, because if I would choose ln to be u, in this step I would have to integrate ln x, which would mean I'm going back to my previous dilemma that I couldn't deal with. So definitely, in this case, what we're going to do is that we're going to calculate and we're going to set v to be ln x. Now, if v is ln x, then dv, which is equal to dv dx times dx, is equal to derivative of ln x with respect to x, which is 1 over x dx, which of course, please remember, we can compactly write as dx over x. Okay, now we need to find u. U is going to be the integral of the other part, which is 1, which is going to give us x plus c. And of course du, which is equal to du dx times dx, is derivative of x, which is simply 1 times dx. Okay, just to make things more clear, I'm going to change here one thing, the order, which of course is irrelevant, just to be sure. Okay, and look, now I can start substitution. Instead of ln x, I'm going to write v. Okay, I'm going to start here, sorry. Instead of ln x, I'm going to write v. Instead of 1 dx, or simply dx, I can write du, which is equal to u times v minus u dv. Okay, so now that we've dealt with this, we can start substituting things back. So u times v is x times ln x. Then we've got minus integral of u, which is x, times dv, which is 1 over x dx. And look, those two cancel each other out. So we get that this is x, ln x, integral of 1 dx, which is simply equal to which is simply equal to, sorry, here's of course minus, is equal to x, ln x minus x plus c, or if we take x out, we get that this is x times ln x minus 1 plus c. And look, what we have actually established from here to here is the formula for the integral of natural logarithm of x. Can we check it? Well, quite easily. Look, if I differentiate this expression, x ln x minus x, okay, let's add plus c. Okay, so how should I do it? Well, look, the first part over here we need to deal with using derivative of a product. So we get that this is ln x times 1, derivative of this one, times a plus x times 1 over x, derivative of ln x, minus 1, and derivative of c plus 0. And look, those two cancel each other out, so we've got 1 minus 1, which is 0, and we end up with just ln x. So we see that the rule that we've obtained just now works perfectly well. Okay, so now that we were able to deal with this case, let's dig a little deeper and try to do something even more complicated. How about we're gonna do a case very similar to the previous one, but let's just say twice as complicated. So we're gonna have to integrate ln squared x dx. Okay, right away, there is a tempting thing to do. Because we've got ln x squared, why not to write it as ln x times ln x dx? Because we have two ln x's. If we have two ln x's, it means we've got two components, one is going to be v, one is going to be u. But look, in order to get u, we would have to find integral of ln x. We know it right now. So we could use it. But let's try the different way. Let's try like a more adventurous way. And our way is going to be write it as ln squared x times 1 dx. So our v is going to be ln squared x. So now the question is, what is dv? dv dx times dx. Okay, and look, if this is our case, we need to differentiate ln x squared, right? ln squared x. So we can do it in two ways. We can calculate it either as a derivative of a product of two functions, right? And then what we are getting? We are getting that this is 1 over x times ln x plus 1 over x, 1 plus ln x times 1 over x, which is 2 ln x over x. Right? Now what we can, the second way we can do it is by the token of the chain rule. And look, by the token of the chain rule, what we're gonna get? Derivative of the, if we assume that t is, for example, ln x, derivative would be 2t, so 2 ln x multiplied by the derivative of the inside function. Derivative of inside function is 1 over x. So we've got divided by x. But as you see, it doesn't really matter, which is, of course, it makes perfect sense. Doesn't matter which rule we are using, we are getting exactly the same outcome. And this is the way it should be. So we've got here 2 ln x over x dx. Then, of course, u is an integral of 1 dx, which is equal to x plus c. This is what we had previously. So du, which is equal to du dx dx, is equal to is 1 dx. Okay, and now we can start substitution. So we've got that this is integral v du, which is equal to u times v minus integral u dv. Okay, u times v is simply x times ln squared x. And now we've got minus integral, and we substitute first u, which is x times, where do we have it? Where do we have it? No, we got x. We've got 2 ln x over x dx. Okay, look, those two cancel each other out. 2 I can take out of the equation, of the integral. Okay, and look, now when we are at this stage, there are 2 things that could be done. Well, the first thing, and I'm showing you this because you might encounter such a problem, here we would have to integrate this one more time. So integrate v1, which would be equal to ln x, and then dv would be equal to dx over x, but this would be dv1. We would have to introduce u, which would be equal again to integral of 1, which would be equal to x plus c, and du1 would be equal to 1 du1. Dx, I'm sorry, du1 dx. And sometimes we need to resort to such technique, but because we've just did it, why not just substitute the result we've got right upstairs? So we will get, we are getting from this, by substituting this over here, that this is equal to x ln squared x minus 2 ln x, 2x ln x plus 2x plus c. Of course, we might get 2c if we substitute it directly or minus the c, but it doesn't really matter. You can simply keep it as plus c. And this is our result. Okay, I know that this is becoming very late for you, but I also understand that getting the hang of integration by parts might take some time, and let's just do one more example. And also rather pleasant and I would say even fun to do. Okay, so now let's just say that we need to integrate expression x times e to the power of x dx. Okay, how do we go about this one? Look, which should be v, which should be x? Doesn't really matter. I think I'm going to choose it like this. That's x, v is going to be x, which means that dv is equal to dv over dx times dx, and u is going to be equal to integral of e to the power of x dx. This is a very clever way because integral of e to the power of x is still e to the power of x plus c. And in this case, du, which is equal to du dx dx, the derivative of this with respect to x is of course ex times dx. Okay, so now we are ready to substitute. So we've got that this is v du, which must be equal to u times v minus integral u dv. Let me just put this over here. And so this is going to be x times e to the power of x. And now minus integral, of course here is just dx. A minus integral of e to the power of x dx, which is equal to x times e to the power of x minus e to the power of x plus c, or simply e to the power of x times x minus 1 plus c. Okay, so this is it. This is all we planned to do at this point. Now, the only thing I want to ask you is to practice it a lot, because the only way you will truly learn how to do it is by doing a lot of problems. Okay, so look, what we've been doing right up till now are not just integrals. Those are called indefinite integrals. I did not introduce this term before because I didn't want to confuse you too much with the new things, but since the next video, we're going to start definite integrals, and then the difference between the two will become self-evident. So thank you for your attention, and see you in the next video.